A payload for GSLV Mark III D2 is a very advanced high-throughput satellite GSAT-29, which is a multi-band, multi-beam communication satellite with a lift-off mass of 3.4 ton. GSAT-29 payloads are configured to cater to the communication requirements of users from Jammu and Kashmir and northeastern regions of India. Apart from these operational requirements, the satellite would be demonstrating several new and critical technologies also.
The first stage of this giant vehicle consists of two S-200 boosters, which are 26.2 meters long and 3.2 meters in diameter. Each has a capacity of carrying 205 tons of solid propellant. S-200 is the third largest solid rocket motor in the world. The L-110 core stage carries 116 tons of Earth-storable liquid propellant. It is nearly 21.4 meters long and 4 meters in diameter. It employs two enhanced thrust Vikas engines. The 13.5 meter long indigenous C-25 cryogenic upper stage forms the third stage of the vehicle. It uses 28.6 tons of supercooled liquid hydrogen and liquid oxygen, which provides more thrust for every kilogram of propellant burned compared to conventional liquid propellants. On top of the third stage is the spacecraft in the 5-meter diameter payload fairing. The first successful experimental flight of GSLV Mark III took place in 2014 when it carried a crew module as its payload. Both its solid and liquid propulsion stages had performed well, and the vehicle was proven in the atmospheric flight regime. The first developmental flight of GSLV Mark III successfully launched India's high-throughput communication satellite, GSAT-19, weighing 3,136 kilograms on 5th June 2017. In this GSLV Mark III D2 mission, the rocket will carry the 3,423 kilogram GSAT-29 communication satellite into geosynchronous transfer orbit. GSAT-29 is a forerunner of future advanced communication satellites of INSAT and GSAT series. Its Ku and Ka band communication payloads are designed to mainly focus on providing high-throughput connectivity to the large population of the country, including the ones in hilly and geographically inaccessible areas of Northeast and Jammu and Kashmir regions. The satellite is also a test laboratory for several new technologies. It is a 3-axis stabilized geostationary satellite configured on ISRO's enhanced I-3K bus. The satellite has a multi-band, multi-beam payload, which is essentially meant for demonstrating new technologies. The Ku band payload of the spacecraft comprises transponders for Northeast and for Jammu and Kashmir regions. The two overlapping spot beams, one each over Northeast and Jammu and Kashmir regions, will provide connectivity between users carrying small terminals. The Ka band payload consists of fixed and steerable beams to serve the country, including the northeastern and Jammu and Kashmir regions. GSLV Mark III D2 vehicle will lift off with the simultaneous ignition of its S-200 boosters. The ignition of the liquid core stage will be at 114 seconds into the flight. Both the boosters will burn out and separate from the vehicle at 140 seconds after liftoff. At 225 seconds, the payload fairing will separate. At 317 seconds, the liquid core stage will burn out and separate from the vehicle. 2 seconds later, the C-25 stage will ignite and will burn for almost 10 minutes. Subsequently, it will shut down at 965 seconds. GSAT-29 is planned to be injected into a GTO with its perigee at 190 kilometers and apogee at 35,975 kilometers. The Master Control Facility (MCF) at Hassan will take over the command and control of GSAT-29 soon after its separation from GSLV Mark III D2. The satellite orbit will be raised to the final circular geostationary orbit (GSO) by firing liquid apogee motor in stages. Once the satellite reaches its final orbit, the solar panels and telecommunication antennas will be deployed. With the success of this flight, the development phase of GSLV Mark III vehicle program will be completed and the vehicle's operational phase will begin.
With Aryabhata, the first Indian satellite, from a simple spin-stabilized satellite in the low Earth orbit to the highly complex interplanetary missions. The evolution of the Indian satellites in the last 5 decades has been phenomenal and astonishing. Today, India is one of the pioneering countries to use satellites for its rapid overall development. It has been a challenging and interesting journey over the years with an array of satellites for communication, meteorological, remote sensing, navigation, scientific satellites, and when it comes to rockets like SLV, ASLV, PSLV, GSLV and GSLV Mark III. The saga of the Indian satellite began with Aryabhata, the first Indian satellite, from a simple spin-stabilized satellite in the low Earth orbit to the highly complex interplanetary missions. The evolution of the Indian satellites in the last 5 decades has been phenomenal and astonishing. Today, India is one of the pioneering countries to use satellites for its rapid overall development. It has been a challenging and interesting journey over the years with an array of satellites for communication, meteorological, remote sensing, navigation, scientific satellites, and when it comes to rockets like SLV, ASLV, PSLV, GSLV and GSLV Mark III. The saga of the Indian satellite began with Aryabhata, the first Indian satellite, from a simple spin-stabilized satellite in the low Earth orbit to the highly complex interplanetary missions. The evolution of the Indian satellites in the last 5 decades has been phenomenal and astonishing. Today, India is one of the pioneering countries to use satellites for its rapid overall development. It has been a challenging and interesting journey over the years with an array of satellites for communication, meteorological, remote sensing, navigation, scientific satellites, and when it comes to rockets like SLV, ASLV, PSLV, GSLV and GSLV Mark III. The saga of the Indian satellite began with Aryabhata, the first Indian satellite, from a simple spin-stabilized satellite in the low Earth orbit to the highly complex interplanetary missions. The evolution of the Indian satellites in the last 5 decades has been phenomenal and astonishing. Today, India is one of the pioneering countries to use satellites for its rapid overall development. It has been a challenging and interesting journey over the years with an array of satellites for communication, meteorological, remote sensing, navigation, scientific satellites, and when it comes to rockets like SLV, ASLV, PSLV, GSLV and GSLV Mark III. The saga of the Indian satellite began with Aryabhatta, the first Indian satellite, from a simple spin-stabilized satellite in the low Earth orbit to the highly complex interplanetary missions. The evolution of the Indian satellites in the last 5 decades has been phenomenal and astonishing. Today, India is one of the pioneering countries to use satellites for its rapid overall development. It has been a challenging and interesting journey over the years, with an array of satellites for communication, meteorological, remote sensing, navigation, scientific satellites, and when it comes to rockets like SLV, ASLV, PSLV, GSLV, and GSLV.
The local organizing committee just wanted to know that whether we shall start the session.
Yes, sir, we can start the session.
Yes. Good afternoon all. So formally, I will welcome all the presenters and audience and a session chair as well as the co-session chairman, Dr. Durga Rao from NARL. So welcome you all to this day 2. We have afternoon session PS5 and we have altogether around 14 lectures from 2 to 6:30 p.m. So it has a break in between 4 to 4:30. So in the first sessions, we have 8 lectures in which I will be chairing as a session chair. And it is a great honor for me to be with you in these sessions. So before I start, I would like to, we have the first presentation invited talk from Dr. Tirtha Pratim Das from ISRO headquarters. And I know that all the presenters know him very well. But as a protocol, so let me take an opportunity to introduce him so formally. Welcome you, sir, Dr. Tirtha Pratim Das to the afternoon sessions. Yeah. And Dr. Tirtha Pratim Das is the director of the Space Science Program Office at ISRO headquarters, Bangalore, India. As a trained planetary scientist, he started his careers in ISRO as a launch vehicle technologist in Vikram Sarabhai Space Center, Trivandrum, ISRO. And he has contributed to the PSLV and GSLV missions while he was working in that team. Subsequently, he actually played significant role while he has been moved to the Space Physics Laboratory, SPL, unit of the Vikram Sarabhai Space Center. And he played a significant role in the planetary exploration program of ISRO and contributed to scientific exploration of Moon and Mars in Chandrayaan 1, 2, and Mars orbiter missions. In the pursuit of the innovative technologies and the disruptive technologies in ISRO, Dr. Das has also been instrumental for the development of disruptive and futuristic space technologies for the new decades. While working in the DTDI, that is the actual Director of Technology Development and Innovations, wherein I am also here. As per academic, Dr. Das is an alumnus of the Department of Physics, St. Xavier's Kolkata College, Kolkata, and Institute of Radio Physics and Electronics, University of Kolkata. He earned his PhD on the lunar exosphere from Cochin University of Science and Technology while working as a scientist in the Space Physics Laboratory, Vikram Sarabhai Space Center, ISRO. So this is a very brief introduction. I understand that he has achieved much more than this. So I don't want to actually, because introducing him will take a long time. So without taking much of time, I would like to open the sessions with his interesting talk on the scientific instrumentations for space missions. Over to you, sir.
Thank you, Raghu. Thank you, Durga. So, Raghu, you may start presenting, start putting my presentation from your end.
Yeah, sure.
And I take this opportunity to thank the National Space Science Symposium organizers to have given me this opportunity to speak on the aspects of instrumentation for spaceborne scientific instruments. When we listened about a major discovery on space science from a spaceborne instrument, we remember the contribution of the final aspects of space instrumentation behind it. It may not be new for the scientists and engineers who are engaged in the development of scientific instruments for space, but I have designed this lecture to reach out to the students and academia and scientists from several institutions who are yet to join the endeavor of developing space-based instruments. So in this lecture, I shall highlight the major aspects of how spaceborne scientific instruments are developed. Next slide, please. Yeah, second slide. Yeah, these space-based instruments improve our understanding of space and hence facilitate improving the theoretical models. So it is an iterative process where theoretical modeling and space-based experiments aid each other. Now, the point to be noted is that each type of measurement in space-based scientific experiments has its own set of spatial requirements and challenges, which make the associated scientific instrumentation special. It indicates that the scientific payloads are significantly different from the standard avionics systems which are used in, say, aeroplanes, rockets, or missiles. Next slide, please. So when we say the standard avionic systems, what do we mean? We mean that the telemetry systems, tracking and command systems, say the navigation guidance control system, power system, to name a few. Point to be noted here is that all of them are mission critical. What do I mean by mission critical? Failure of any of these systems may jeopardize the entire mission. These systems are often equipped with redundancy to address failures. Now the question is, what make the scientific payloads so special? So when you compare the avionic systems vis-a-vis the scientific instruments, where do the scientific instruments find their place? So next slide, please. So when it comes to the scientific payloads, a common set of rules which apply for the avionic package, conventional avionic packages, they do not apply. Some of the scientific instruments may have to handle weak signals from space. Some capture sporadic events. Some of them may be sensitive to contamination, spacecraft charging, magnetic fields from the spacecraft. I can name, it is a big list. To make it more complex, in many cases, the scientific payloads may not be completely testable under realistic conditions, as it may not be possible to simulate exactly the same conditions they are going to experience in space. To add to that, scientific payloads in general do not have redundancy, as they're usually not mission critical like the avionic systems. Next slide. So scientific instruments, therefore, cannot be stereotyped. While some of them are meant to make continuous observations, like, say, solar wind observations from the sun or radiation emitted by the celestial bodies, there are payloads or scientific instruments which are meant for capturing the sporadic events like, say, coronal mass ejection from sun or ionospheric scintillations, gamma ray bursts, to name a few. Similarly, the signal they are expected to receive, they may be feeble, like sampling the upper atmosphere of the planets, or the signals may be strong, like the imaging of reasonably bright objects. Some of them function in active mode, like radar-based probing, while some of them have to depend on the subject under study to emit some signal, like the passive remote sensing. While some of them have to depend on like emissions to come, like, say, X-ray fluorescence coming out of the surface of the planet in response to the solar X-ray flares. So this diversity makes them different in terms of their production, their characterization, calibration, special protections they need, to name a few. Now, if we compare this scenario with the avionic systems, the differences are quite evident. Avionic systems in general have guaranteed inputs to have to face lesser surprises. Next slide. So there are several other challenges while designing a scientific payload. Often, one needs to do a trade-off between resolution and throughput, which is very common in spectroscopy instruments. More accurate spectral information by achieving high spectral resolution comes at a cost of the proper throughput. That is, your signal strength will not be sufficient. If you do a very high quality filtering to get a very good quality of spectral resolution, you may have to compromise on the inputs to your detector. Then you have to go for a very high gain detector. There will be some associated problems creeping in with that, with respect to very high sensitivity of the detector, which may suffer from the problem like instability or high inherent short noise. Okay, go to the next slide. Yeah, so yet another challenge is to compromise between the range of the measurement and the resolution. So if you're planning to measure the energy distribution of a group of particles, let us take this example, you may like to cover a broad band of energy, and that too with a very high energy resolution. Now, nature doesn't offer the luxury of for a single detector, and you may either have to compromise on the energy range to cover or the energy resolution itself. If you cannot compromise either, you may have to opt for multiple instruments or multiple detectors. And they come with their associated problems like inter-channel interference. If you're having a multi-channel instrument carrying the outputs of different detectors coming, there may be interference between the channels, and increased complexity of the instrument, high mass and power requirements, to name a few. Hyperspectral payloads have already been flown in space missions, and the successful development of these kinds of instruments poses numerous challenges. Next slide. So yet another decision needs to be taken about the compromise between the dynamic range versus sensitivity. Now, what is dynamic range? Many of you remember that dynamic range is often described as a ratio. It is a ratio between the maximum to the minimum strength of the stimulus, that is the signal to be measured. In any instrument, the minimum measurable signal is limited by the system noise, while the maximum strength, maximum measurable signal is limited by the detected nonlinearity, highly elliptical orbit around mass. So see, how does a concept, what I want to do, what is the problem, what should I do, where should I do, how this is taking the shape of a mission idea. Okay, now go to the next slide. Now, having started from this bigger perspective, then it is the time when one goes on narrowing down the idea and addresses the specifics. So a few generic steps I have mentioned here. So the first step is you begin with an open problem in sights, and as a second step, you ask what are the physical parameters you need to measure to address this problem. Now, after having identified the physical parameters, then the question is, what kind of instruments are needed to make those measurements of these physical parameters? Now, should it be done from an orbiter? Should it be done from a lander or rover? That you have to think. And then, after having that job done, the next step is you have to quantify the instrument specifications. And then, after having quantified the instrument specifications, you have to think how to make it a part of the spacecraft or a lander or a rover or an impactor. So your instrument becomes a payload. Okay, so this is how the logical flow comes into the picture. Next slide, please. So in the step 2, after having the scientific thought and the idea, you have to write down the idea in terms of a proposal. You are going to share the idea with the scientific community. So you may have to wait for an announcement of opportunity. And then what happens, I will tell you, go to the next slide. So in the second step, what you do is, when you are writing down the scientific proposal, we often wish to pin down the ideas, but many of us are not sure about what all we need to mention in a scientific proposal to fly an instrument to space. And that is not a problem because many of us have done it for the first time. For all of us, there have been some first time. So the members of the academia institutes who are listening to this lecture may find it useful that if you are planning for a scientific instrument to fly to space, so what are the things we look for when you write a proposal? So it is very important to follow those because the committee that reviews the proposals, they look for a few specifics, without which the proposal cannot be evaluated. So a few of the generic points I have included here, like the scientific objective and the context and relevance of this scientific study, literature review, some work might have already been done in that area, and what new you are going to expect. Emphasis has to be there on that. And in order to study that new thing, which you are thinking that new thing should be studied, what are the observation requirements in terms of the platform, orbit specifications, etc.? What are the specifications of the instrument which you are going to propose? And what are the resources you need from the spacecraft, like the mass of the instruments which you are planning, the power it is going to consume, the volume it is going to occupy, the bandwidth it is going to eat. And if you are going to have propose some instruments, there is something called technology readiness level. So this itself is a topic of lecture which I will not go. If you are not aware, please Google it. What is meant by technology readiness level? There are 9 levels according to the definition. And whether you are going to start afresh or already you have done some progress and you wish to make it a scientific payload, and if your proposal is selected, how much time will you need to deliver the instrument? That is called the turnaround time. That is also very, very much important parameter. Now, the facilities which are required to develop that instruments, whether your institute already has those facilities or you have to collaborate, that also you may have to indicate, and the expertise and experience available with the team and the budget requirements also comes as a part of this. So this is roughly the thing. So coming to the designing part of the instrument, next slide. See, this is not a lone traveler's job. So far, the scientific idea was in paper and the PowerPoint presentations. Now, when it comes to the level of materialization, when it has to be materialized, it is no longer a lone traveler's journey. Realization of a scientific instrument for space-based exploration is a teamwork. The team that takes up the job of developing the scientific instrument is often termed as the System Development Agency, or SDA. SDA functions with a perfect balance of 3 facets. One is science, other is technology, other is management. And this SDA comprises the principal investigator. There may be co-principal investigators, there will be project managers, deputy project managers, and there will be the team members. So all of them have to do a perfect balance of the science, technology, and management. Next slide. Yeah, as you're aware, the designing any scientific instrument starts from the generation of the specifications. So having gathered the specifications, the generic steps are the design of the sensors, choosing the suitable detector, and last but not the least, the mechanical design of the system. So in this process, what happens? The modeling and simulation play an important role, especially in the sensor design and the mechanical system design. In our design philosophy, we ensure that the best quality practices start from the most fundamental level, like it starts from the materials, and then the hierarchy starts going from the basic to the above, devices, circuits, and systems. Now, once you design the scientific instrument, you develop the what we call a prototype or engineering model or the proof of the concept model to start with. And the 4th step in the journey is the demonstration of the proof of the concept. Next slide, please. So now, when we are telling that you have to develop the proof of the concept, you have to show that whatever you have thought, the system really works. Okay. Now, demonstrating this proof of the concept of a spaceborne scientific instrument is a challenging job. It is challenging because often you may not be able to simulate all the conditions in which the instrument is supposed to function. So there often exists a limitation in the conditions while you demonstrate the functionality. To address this, sometimes you may try simulating some conditions in some specialized chambers or perform a sounding rocket experiments, to name a few. And many of the times it is not possible that you simulate all the conditions simultaneously. And that is critical because all the conditions may have dependency on each other or one another. So when you are isolating one condition and you're testing the system response with respect to the other, it will not give you the proper picture. So always there is some limitation, and that's why the importance of the good facility for testing a scientific instrument comes in. To whatever extent you can test the system close to reality. Next slide. Now, those who are going to do the proof of the concept demonstration for the first time, for them, I have prepared here in this slide a generic list of steps. You start from a qualitative stimulus response check. That is, you have input and you have your output. You change your input to see if there is any change in the output. You don't bother about quantifying it. In the second step, you quantify it. That is, you quantify the response for a given amount of stimulus. As a third step, you use a standard input and check the output. So what do I mean by a standard input? Standard input means, let us take an example. When I say 1 kilogram, okay, it is a standard. 1 kilogram has a meaning. Or if I say 1 ampere of current, it has a meaning. So that standard stimulus, if you put and see how is the output of the instrument, and this process is called the calibration. And this setup is called the calibration setup of the instrument that all of us are aware. So here you are also going to test a few important facets in this process, like repeatability, stability, precision, accuracy, linearity of the instrument, to name a few. Next slide, please. Now, so far we have been talking about the proof of the concept of the instrument, which is basically a laboratory-based instrument. After having demonstrated the proof of the concept successfully, the next step is to define the interfaces of the instrument with the observation platform. The observation platform could be a spacecraft, a lander, or a rover, so on and so forth. Whatever is the observation platform, the proper interfaces of the scientific instrument have to be defined. Now, when I say interfaces, I mean the power interface where the DC-DC converters are used rather than the laboratory power supply. There are telemetry, tracking, telecommand, and data interfaces for remote health check of the instrument rather than connecting it to a desktop PC. Changing the operating modes with the telecommand, as well as the acquisition of the scientific and housekeeping data. So there is also a mechanical interface to mount the scientific instruments on the observation platform. Next slide, please. So all these interface-related aspects are captured in a document called the Interface Control Document, or ICD. Now, ICD addresses the aspects of this mechanical interface, thermal interface, electrical interface, telemetry, telecom, data interface, as well as the checkout interface. Now, the thermal interface, which I mentioned in the slide, that arises due to the fact that any electronic system generates self-heat. The heat dissipation from a scientific instrument is an important parameter which comes under thermal interface. And thermal interfaces address the aspect of sinking the heat generated from the instrument, which comes under the thermal management aspects. Coming to the checkout interface, it is one which simulates the power and the electronic interfaces of the observation platform. So before you connect the instrument with the actual observation platform with actual interfaces, the instrument is tested with simulated interfaces, which is referred to as the checkout system. Those who are into the business are well familiar, they don't need, but I have designed, as I told, this lecture for a general academia and students who will come to the space science instrumentation during their career. So next slide, please. So next comes to a very important aspect. We'll come to the very important aspect of quality management system. And as you know, the scientific payload usually does not have any redundancy, I have mentioned, and hence one needs to have a clear plan of action to develop such an instrument. Next slide. So this slide, almost all of you are familiar with. This is the bathtub curve which you must have studied when you have gone through any lecture on system reliability. So as all of you are aware, any system has got a bathtub-shaped reliability life cycle. The failure probability is high initially, especially due to the workmanship defects, as well as during the fag end of the expected lifetime due to aging, wear and tear. The useful life period is the one which is in between these two regions where the instrument functions reliably. Reliability engineering is a part of, the part and parcel of the design of the instrument, as well as the other protocols for the development of the instrument, operation of the instrument, and also the maintenance of the scientific instruments after having it launched in orbit. Next slide. Now, in this connection, two concepts are of utmost importance. Okay, I think you just go to this slide so that all the things come, because I think this is coming as an animation. Next, one more click. Yeah, that's all. Okay, hold there. So in this connection, there are two concepts which are of utmost importance: the quality and reliability. As you are aware, reliability is a probability that a system satisfies its performance requirements during the intended operational lifetime under certain specified environmental conditions. And as you can guess, it is a long-term concept. The term quality, on the other hand, refers to conformance of a system to its desired specifications. So when you have designed your scientific instrument, you have certain specifications in your mind. Whether your system is adhering to those desired specifications, that is quality. So a good quality assurance plan is followed for the development of the scientific instruments, which is necessary for ensuring its reliability. Okay, so user satisfaction is quality at t is equal to 0, and when you extend to t to infinity for longer time, we call it reliability. So reliability is in the time dimension, quality in the time dimension. So here also you go to the all the animations. I think that's all for there. So while the maximum value of reliability is 100%, in actuality the reliability of a real system is less than ideal. If a system is designed for 90% reliability, after actual reliability, you may achieve 80% for the proto model. Now you have to improve the reliability by proper engineering practices, like review mechanisms, addressing the different detection of different failure modes. Wherever required, you redesign the problem areas, retest, and so on. So when you adapt all these mechanisms for the scientific instruments, the reliability of the subsequent models may be improved. Okay. Now, this whatever I'm telling holds good for the avionics systems as well. But avionics systems, the difference is these systems are prototypes. You may not have to de-engineer, redesign the whole thing from one mission to the other. But when it comes to the scientific instrument, every time you make such a scientific instrument, these facets have to be relooked. That is the major difference. Next slide. So this is precisely the idea behind the concept of the model philosophy. Many of you might have heard about the term model philosophy in space-borne instruments. The prototype or engineering model is followed by a qualification model. The qualification model in turn is followed by the flight model. The performance of the engineering model is reviewed in the preliminary design review, PDR, and the recommendations of the PDR are addressed in the qualification model. Now the qualification model is tested. You will definitely see some improvement when you have incorporated all the recommendations of the PDR, and the performance of the qualification model is reviewed in the critical design review, the CDR. And this is followed by the flight model. So this is the model philosophy usually followed in any space-borne instrumentation. Next slide. Now this philosophy, model philosophy, guides the product life cycle of any scientific instrument. You start from the scientific requirements, and there is a system concept review. After the system concept review, you realize the proto engineering model and test it. And after testing it, the engineering model is subject to the preliminary design review. And if the preliminary design review committee suggests some improvements, you go back to your engineering model. And once the preliminary design review is done successfully, you come to your qualification model development. You test your qualification model and you subject it to a critical design review. And again, the critical design review may have some observations. If there are some suggestions or improvements suggested, you go back to the qualification model. And then once the CDR committee is satisfied, you come down and develop your flight model. And identical procedure has to be followed, whatever you have followed to make your qualification model for the flight model. And after the flight model is developed, this flight model is eventually going to sit in a spacecraft or a lander or a rover. Okay, so there should be a pre-shipment review. This is mostly for the conformances and interest-related things. And now in the question question is how to extend the useful lifetime of a scientific instrument. So as I mentioned, adherence to the quality leads to the better reliability. and extended period of user lifetime. The quality is achieved in 4 steps. The first step is, quality planning. So quality planning is done by a quality assurance plan. So wherein you address all these aspects like design, material selection, drawing, reviews, acceptance tests, all these things. And this quality assurance plan forms a baseline document for quality assurance and resource management. Next comes the next step. You go to the next slide. Yeah, the next step is quality control. So it is the implementation part of the quality management system, wherein what you do online inspection, okay, and inspection of materials, which may include the non-destructive tests wherever necessary, online quality inspection during the manufacturing every steps, and final quality inspection after the realization of the entire systems. So this is the step wherein you are implementing, you are doing the things. In the first step you planned, now you are doing it. Next slide. So as a third step, you are ensuring that your things are done as per the plan. So to ensure that quality assurance plan as per the agreed baseline document is implemented in all stages, you have to get back and check whether these things are done properly by checking of the design inputs, design the checks from the reliability analysis aspects, quality assurance audit of the process, and issue of the quality assistance report is very important. You may think, I'm flying a scientific instrument. Why do I have to do all this paperwork? This paperwork is very important, which I would like to impress upon through this lecture. Okay, go to the next slide. So then comes the quality improvement for the design with the design reviews and removal of non-conformances. Often what happens, this step happens as a lesson from the present mission, which is useful for the subsequent mission. And quality is a never-ending process. In the 4th cycle process, it goes on and goes on and goes on. Avionics systems have undergone this step over years. For the scientific instrument, every time you are freshly seeing the face of the bride. It is happening in that way. So next slide, please. Now, then comes next slide. Design margin validation to test the robustness. What happens is, now that all the quality norms are followed and the scientific instrument is developed, it is necessary to validate its design margin. The design margin is a measure of the robustness of the scientific instrument, which is measured by the ratio of 2 quantities. Again, in the numerator, you have the amount of the load, which could be the current or the mechanical load, where the system fails. In the denominator, you have the nominal or the expected load during the mission. And the design margin is obviously greater than unity, but often less than 2. 1.4 or 1.5 is a very good number to avoid over-design and associated complexities. We cannot do an over-design and make the system very heavy or very, very complicated. Next slide. And there are different kinds of environmental tests that are very important in the whole phase, the launch phase, and for commissioning phase, and in the mission phase. And what happens is this design margin when you are testing, when you are telling that I am testing the design margin, you are doing a destructive test. You are allowing the system to fail. Often that we don't do. What we do is we do a validation of the design margin by doing a non-destructive testing, and which is economic and which saves your time also, so which is schedule friendly and validates the lower limit of your design margin. If it is 1.4, you have tested your system, you are confident my system will not fail if the design loads are more than 1.4. That kind of a thing to do. Next slide. And which is often done by the environmental test level. There's a committee which tells if I launch with a PSLV or GSLV, what are the kinds of vibrations is expected, and what are the kinds of loads are expected at different phases. And accordingly, the test and evolution specifications are generated, which gives rise to a document, T&D plan. Test and evolution happens, and these inputs from the system development agency and the system reliability entity, they work hand in hand to do this environmental test, and which is an input to the critical design review, CDR. Next slide. I'm running short of time, so I will be hurrying. Next slide. Yeah, coming to the flight model realization, one thing we have to remember that whatever procedure you have followed to develop your qualification model, after that, you don't do any changes while you make the flight model. And when you test the flight model, the designer level characterization tests you have to do, system noise, sensitivity, gain, nonlinearity, linearity, resolution, all these things. Ground calibration you have to do, and tested evaluation when you do, qualification models are always over tested. You have to do a testing at the 1.5 times of the nominal flight loads which are expected. But don't subject the flight model to those levels. So you cannot send an over tested model to space because its useful lifetime may be less. And post TNT characterization you have to do and calibrate the thing. And in this, we will stay here. So we are not going to read this slide. What the message which I would like to convey here is, in this whole process of development of the instrument, you generate lots of documents. And in what stage of the process life cycle, which documents have to come, I have mentioned here. Anybody who is doing it for the first time, and those might have been doing this thing for a few times, may treat this slide as a reference, as a checklist, whether you have all these documents for the instruments which you want to fly to space. Next slide. Now comes the system level testing. So what we do with the system level testing, the flight model is transported to the spacecraft integration clean room. And there we do a post-transportation benchtop test, which is limited to the package level test. Very minimal things are done. And then this is electrically connected to the spacecraft or whatever platform you're going to use. And they are not mechanically mounted. And after having this done, you mechanically mount it and see. And after that, in the integrated environmental test at the spacecraft level, you perform. And sometimes you have to test for the special storage conditions. Have some special storage conditions. That is very much instrument specific. Okay. And here, it is a coordinated effort, and I have mentioned all the spacecraft, mission, project team, ground segment, launch vehicle team, all these people have to coordinate with different payloads. A given mission is not going with one payload in general. There are multiple payloads, and it is a connective team activity. All these payloads people are connected with all these teams in a coordinated harmonic symphony. Next slide. Now, when you are at the middle of the discussion, you are a system development agency, principal investigator, you are interacting with mission team, you are interacting with the project team, you are interacting with the ground segment team, you are interacting with the other payload teams. And here, this slide, if you keep it as a reference, this will tell you what kind of information should go from you to the others and what kind of information you may need from the others. Okay, this I'm not going to read out, but just to give you a feeling, what are the things important here. Coming to the mission operation phase, go to the next slide again. So data archival, so you have sent the mission to space. You have started getting the data. Now, what are the things important? Data archival, ethics and policies. The archival, efficient storage mechanism, data dissemination, standardization of your data storage, repository for generations to come. Because once you have sent a mission, generations after generations will use the data. So there should be standardization. Ethics means correctness of the data, completeness of the data, and declarations of limitations, if any. We call them caveats. Coming to the policies, which level of data you are going to give, whether you are going to give raw data or some process data. Any lock-in period is there, that is within 1 year I will not give, after 1 year is over I will give, that kind of policy. How will you disseminate the data? Those modalities also are coming. So these are all policies. Next slide. So data archival details, okay, this I will not go dwell into this slide. These are too much details on the data levels. So I conclude with these slides. Yeah, you go to the black colored slide, yeah. So the take-home message. A great discovery is made after a planet is probed by an instrument which is calibrated to the best possible accuracy with its design margin speaking for its reliability, which is designed to meet the stringent specifications translated from a scientific concept silently born in the mind of a scientist. So how this journey evolves and how the things take place, if you keep this as a reference, I am sure many of the students and scientists or faculty from academia also, after a few years, will join the league to develop scientific instruments for the space missions. Thank you very much for being with me. Jai Hind.
Thank you, sir, for your very informative and scintillating talk. Basically, it was like just a journey from the conceptualizations of an idea to the realizations of subsystems, and even after the mission also how to get the data and disseminate the data. It was a step-by-step guide for the beginners, designers, and the engineers. So just I want to hear from my co-chair a few words from Dr. Durga Rao. Over to you about the talk.
Yes, sir. It's a very interesting talk. And right from the conceptualization in the silent mind of a scientist to the realization to the invention, very nicely explained. This will be a general guideline rather than because most of the scientists, when they are an engineer, when they conceptualize the design, so they don't know how to really it will be transformed into a payload because up to engineering model is only be done in some cases. So in that, very nicely it was explained. I think even from the chat box also, and some of the questions are there. So probably 1 or 2 questions we will take based on the time. It's a very nice talk, sir, and I'm hand over my thing to chair. Sir, you can read out some of the questions.
Yes. Thank you, Dr. Durga Rao, for your words. And now the session is open for 1 or 2 questions because we are running short of time. And just let me see the questions available in the chat box. Okay, just 1 minute. So one, actually, Mr. Barun Bolero was asking that it was a nice talk and would like to get these slides, whether it will be available or not. So probably, I think with the kind permission of the organizing team, probably I think that it will be available. So that is my understanding. So Dr. Barun.
I understand this is being streamed to YouTube and YouTube videos remain.
Yes. Yeah, thank you. And okay, Dr. Binit also, the same thing, it is available in the YouTube. Yeah. Then I think now 1 or 2 questions we'll take up from the audience. Any questions from the audience? So I think there is no further questions from the audience. I understand that the talk was very interesting and it is very
I have a small question, sir. Can I ask one small question, sir?
Yeah, please go ahead.
Yeah, you mentioned about announcement of opportunities. How frequently this announcement of opportunity comes, and what is the basis of creating this AO?
So what actually happens is it is linked with the scientific requirement. Suppose there is a scientific community telling, I want to explore, suppose, say, planet Mercury. Let us take an example. And scientific community will tell, okay, I want to study these parameters of Mercury. Then once we think that, okay, these kinds of instruments should study, then there will be an announcement in the ISRO website that, okay, these kinds of parameters are going to be studied. Anybody is having some expertise to develop some instruments, or this is one kind of announcement of opportunity, which comes from the payload development point of view. Another kind of announcement of opportunity is that payload has already been developed by somebody or will be developed by somebody. There may be a community involved who will be interested in the data from the instrument. They are not developing the instrument, but they will be interested to use the data. Okay, these kinds of announcement of opportunity will come in the ISRO website. Okay, and through that there will be instructions given, and accordingly you have to act. But this lecture tells about if you are playing a role of a system developer. Suppose you are responding to an announcement of opportunity wherein an instrument is asked from the community, what are the things you have to do, what are the things you have to put in a proposal, and how the journey looks like. Okay, I hope I could answer your question.
Yes, sir.
Yeah, thank you for the clarifications given to the question.
Sir, I'm Dhanya from SPL. Can I ask one question?
Yes, yeah, Dhanya, Dr. Dhanya, please go ahead.
Yeah, thank you, sir, and thank you, Dr. TP, for the wonderful talk. It was so nice. And I have one question. Generally, in the system reliability, you have explained about the bathtub curve. And generally, we see in many occasions that a mission which is designed for 2 years, it exceeds its lifetime and serves 5 or 10 years like that. Even every payload also. So does it mean that we have qualified the payload for a part of the bathtub only? So still they were remaining. That bathtub period is so long that they can survive more. Is it like that?
It is like that, but at the same time, we have to see a fundamental problem. When we speak about the bathtub curve, it is a concept of reliability, and reliability is probability, and probability is statistics. And statistics is all about ensembles. It means that suppose you are flying a scientific instrument which has worked for 7 years, let us say. That means that that particular individual instrument is working for 7 years, but that in turn does not tell that system reliability bathtub curve extends up to 7 years or so. Suppose if you could make 100 such instruments, or 1,000 or 10,000 such instruments, identical instruments, subjected to some testing, and then see how many of them failed after 5 years, 6 years, 7 years, you can make a distribution kind of thing. From one instrument, you can tell, okay, this instrument has survived 7 years. It may survive 1 more year also. But that does not tell anything about the system reliability of that kind of instrument. I hope I could explain.
Yeah, got it. Yeah, thank you.
Thank you.
Thank you, Dr. Dhanya. We have one, actually, it is like information only. This Sri Binit Balsan is asking that can we use some of the ISRO's resources like testing facilities if our institute does not have that one. So probably this Binit, just to answer your question, because the head of your institute, like director or the principal of your organization, should write through proportional to the director of the center. Okay, that is the channel, and of course, based on the approvals of these authorities, competent authorities, this option is also available. So you have to approach to that way. Okay. Yeah, I think we are running short of times, so let us take this opportunity to thank the speaker once again, Dr. Pratim, Director, Space Science Program Office, ISRO Headquarters, for his very interesting and informative talk, which is very actually insightful. So I understand that his talk will be beneficial to the beginners, to all the designers as well engineers, for all the scientific enthusiasts in the ISRO community as well as the academics. So thank you, sir, for your interesting talk.
All the best.
So we'll move to the next talk. So we have very quick, actually, the presentation kind of things. The 4 presentations from 2, 3, 4, 5. Okay, these are very quick presentations. Actually, the organizers have given 2 minutes, but I think let us give 1 minute extra, 3 minutes to them, because we will probably 1 minute we may take a question answer also. So let us welcome Dr. S. Aiswarya from ISRO. So his quick presentation is the design studies on MEMS quadrupole mass filter for miniaturized mass spectrometer. Is the speaker available?
Yes, sir. Am I audible?
Yes, you are audible. Please go ahead. If you have any presentation, you please upload.
Yeah, I do. Is my slide visible?
Yes, you are visible. Yeah, please go ahead.
Yeah, okay. Myself, Ashwath, on behalf of the MEMS division of LEOS, would like to introduce our efforts in developing a miniature mass spectrometer. The enabling technology used to miniaturize is silicon micromachining in MEMS. This approach helps to develop a light and compact instrument with low power consumption. Also, it can operate at relatively high pressure than its macroscopic counterparts. The first step in miniaturization is to develop the quadrupole mass filter component using MEMS technology. This filter is with scaled down dimensions, is modeled in Simian software for an electrode length of 30 millimeter diameter of 1 millimeter, and an operating RF radio frequency of 6 megahertz. So I have presented 3 observations based on the simulation results obtained. So firstly, we have the effect of aperture size of the filter. It is observed that the ion transmission is better for ions that are closer to the central axis of the filter. In our design, the aperture radius we have chosen is less than 25% of the inscribed circle radius. And the second set of simulations is to find an optimum axial ion energy that drives the ions through the filter while achieving satisfactory transmission and filtering action at the same time. The third set of simulation results show mass dependence on the performance of the filter. It is observed that for set operating conditions that is predefined, better filtering performance is observed for lighter ions than the heavier ions in the mass range that it is designed for, which is 1 to 300 AMU, atomic mass units. This means that operating conditions in the heavier domain of the mass range must be fine-tuned accordingly. So we have an in-house MEM fabrication facility at LEOS, and our ultimate goal is to realize a miniature quadrupole mass spectrometer to function as a science payload for future missions of ISRO. Thank you.
Thank you, Dr. Aiswarya, for the quick presentation. It was very informative. Though you have only one slide, you have put everything in all together. And we know that this MEMS QMS is a very good development. Okay, taken up at LEOS. And you know that the MEMS, the advantage is because it can relatively work at higher pressures compared with the conventional mass spectrometers. So these realizations will take us to a new height in ISRO's QMS technology. So please continue your work. And any quick comment from my co-chair, Dr. Durga Rao?
Sir, nothing, sir. You can carry on to the next one.
Okay, yeah, thank you. So one quick this question, so we can take up from audience if anything. Only one question. Otherwise, we'll move to the next presentation. Next talk. Okay, I think there is no questions from the audience. Then let us thank the speaker, Dr. Aiswarya from LEOS. Thank you, Dr. Ashwath. Please be with us. We have 6 more presentations in this session.
Yes,
okay.
Thank you very much.
Thank you. So let us go to the next sessions. Next presentation, electronics development of neutral and ion mass spectrometer from Dr. Piyush Sharma, PRL. So over to you.
So is my slide visible?
Yes, your slide is visible, but the audio is feeble.
Okay, so I'll try.
Yeah, you have to speak a little louder.
Yeah, so hello everyone, my name is Piyush Sharma and I'm working in PRL. So currently me and my team have been working on the development of NIMS, which is neutral and ion mass spectrometer. So today I'll be discussing about the electronics development of NIMS. First of all, what is NIMS? So I'll briefly introduce you to the mass spectrometer, which is using a quadrupole technique, and it can be essential to measure neutrals and ions both for the future planetary missions. So here we can see the block diagram. So in the block diagram, we can see there is an entrance grid, and afterwards there is a quadrupole rods also. So these are the specifications of NIMS, where we are going from mass range 2 to 200 AMU using mass resolution of 0.5 AMU. We have using the detector of Faraday cup and the CEM detector. The total mass is proposed for 2 kg and the total power is 20 watt. So this was the introduction, and afterwards I'll be discussing about the part-wise electronics development. So here are 5 essential parts which needs to be developed. One of them is RF circuit for mass filter. Afterwards, there is a HV circuit for the detector biasing. Then after detecting the ions, we'll be using pulse readout circuit to detect ions as well as control it. And afterwards, we are using the controller card to introduce and interface our front-end electronics with the existing processing electronics. And we can control our inputs using LabVIEW model also. So afterward, the part-wise development, we have developed the in-house developed electronics. Here we have integrated all the part-wise developments, and from the integrated electronics, we have we have our initial results. So in these results, we can see that the gases which were present in the test chamber, we can see the spectrum of those gases. Here we can see around 18 and 28 are present, and 44 is also present. So with this brief introduction, I'll invite you to visit my poster, where queries and doubts are solicited, and you can reach out to me through my email, which is mentioned on the poster itself. So thank you so much. Over to you, sir.
Yeah, thank you, Dr. Piyush Sharma, for your very quick and very insightful talk on electronics developments of neutral and ion mass spectrometer. I have one just questions that whatever 2 kg you have mentioned, is it all in electronics or is all together that spectrometer mass?
Sir, this is electronics plus the detector section also, the mechanical section also.
Okay, okay.
Yes, sir.
Yeah, then I think I will leave to the audience any quick question from. Okay, if there is no questions, I have one more questions, just for my knowledge only. So what is the difference between this neutral and ion mass spectrometer, and what about QMS flown in our Chandrayaan 1 and 2?
So basically, the mass spectrometer which we are developing, it will be detecting neutrals as well as ions both. So it will be very essential for the in-situ development of the planetary atmosphere, where we can have ions as well.
Okay, okay. So the other one is only the neutral. This will have the ion on, correct?
Yes, sir.
Okay. Yeah, thank you.
Okay,
then,
thank you,
yeah, thank you. Let us thank Dr. Piyush Sharma for your presentation. Please continue with your good work. And we'll move to the next presentation, that is graphene-based soap X-ray windows. The presenter is Dr. Aiswarya, PS from the Christ University. I understand that Christ University is in Bangalore. So, Dr. Aiswarya, PS, are you available?
Yes, sir.
Oh, ma'am, yeah, just please over to you, ma'am.
Yeah. Can you see my screen, sir?
Yes, yes, we can see the screen. Yeah, please go ahead, ma'am.
Good afternoon, everyone. I am Aiswarya PS, BSc student at Christ University. I'll be giving a brief insight about graphene-based soft X-ray windows, an ongoing project under guidance of Dr. Christy Thomas Cherian, Department of Physics and Electronics at Christ University, and Dr. Shyama Narendranath, ISRO UR Rao Satellite Center. Soft X-ray windows are very crucial in planetary remote sensing, as celestial bodies emit wavelengths in soft X-ray range. Spectrometers for spatial exploration, such as Chandrayaan-1 X-ray spectrometer and Chandrayaan-2 large area soft X-ray spectrometer, used very thin aluminum filters supported on a polyimide film as X-ray windows. For light element detection, many windows were designed, but all exhibit one or the other setbacks, such as reduced temperature stability, low mechanical stability, etc. As we discussed in the introduction part, X-ray transmission window materials should possess properties like vacuum encapsulation capability, light blocking capability, non-toxicity, etc. The existing materials include beryllium, lithium, polymers, silicon nitride, and graphene. The merits and demerits of all these materials are mentioned in the list given. From the primary results, it is understood that graphene has many advantages over the others. But as many studies prove, the major issue with CVD graphene is that it peels off from the substrate under differential pressure. This is when we tried to modify graphene to graphene oxide and then to reduced graphene oxide to improve its properties. Different techniques like vacuum filtration was used for this. Moving on to results and discussions, we could see that graphene oxide membranes possess many ideal properties like high mechanical stability, chemical stability, and high X-ray transmission. Graphene oxide is an insulator, whereas reduced graphene oxide membranes are electrical conductors. Moreover, as shown in the graph plotted by R.R. Nair et al. From his studies, these membranes are impermeable to gases. In addition, these membranes are industrially scalable too. From all these character analysis, we found that graphene-based membranes are suitable for many applications, and hence we tried fabricating them. The cross-sectional SCM image and image of the film fabricated is given in the figure, as you can see. Hereby, we propose gas-tight graphene-based membranes as a prospective material for soft X-ray transmission windows. Thank you.
Thank you, Dr. Aiswarya, for your very quick and interesting talk. Basically, we understand that graphene is a one-dimensional structures, and then it has a lot of prospects for various applications. And you have come up today with graphene for the soft X-ray windows. So just any quick comment from my co-chair, Dr. Durga Rao?
Yes, sir. It's a nice work and nice study also. And do you have any applications where you are going to use this?
Yes, this is going to be used for all these X-ray windows, especially in space, and for as we mentioned, such windows were used for Chandrayaan 1 and Chandrayaan 2, but the issue was that they used aluminum filters. So if we came up with this and we can modify it better, it will give a better properties for soft X-ray transmission windows.
Okay.
Yeah, thank you. And questions from audience? Okay, if there is no questions, I have one, two comments. It is not a questions. So, Dr. Aiswarya, this graphene fabrication you are telling where you are planning? No, which method? Is it a chemical method or CVD you have mentioned?
Yes, sir.
Can you just please tell one, two?
So we are using vacuum filtration to produce this from graphene oxide membranes.
Now, is it are you having the Chris University is having a facility? That I wanted to know.
Yes, sir. We just the image shown was the film we produced.
Okay. So that is a really good, because you are having facilities, so you can actually do such kind of fabrications and then do analysis, the TM and kind of things. Correct. So
Yes.
that is one part. Another part is this graphenes, depending upon this one, because the atomic arrangements. So is there any a selective the transmission kind of things for particular X-ray wavelength? Can you just tell me 1-2 points in that?
Sir, can you repeat?
No, my question was because this graphene is a one-dimensional structure depending upon these atomic arrangements. Okay. So whether you are having some particular selective transmission.
Yeah, they are impermeable to gas and water, but they are selectively permeable to this X-rays.
Okay. So what is the particular that X-ray wavelength? That only my question was.
Oh yeah.
Do you remember? Or otherwise, okay, we'll leave it. Huh?
Yes.
Yeah, you can actually come back later also. Fine, then.
Thank you.
Let us thank the speaker, Dr. Aiswarya PS. It is very good work, and basically this graphene technology you are bringing for the X-ray, the astronomy. So it is really good. Please continue with your good work and be with us till the completion of these sessions. So now let us move. Yeah, thank you. Now let us move to the next speaker, that is Dr. Kiran M. Jayasurya from ISRO, and his talk is on modeling in orbit radiation environment using GN4 simulators for the XSPECT instruments. So over to you, Dr. Kiran.
Is the slide visible?
Yes, visible. Yeah, thank you.
Okay, then I'll begin. XSPECT is a soft X-ray spectrometer on board the XPOSAT mission. The above image shows the XPOSAT spacecraft with the 2 detector packages of XSPECT. XSPECT will be operating in the 0.8 to 15 keV energy range. The expected background radiation onboard XSPECT needs to be estimated for planning our onboard observations. For this purpose, we imported the CAD model of the XSPECT payload into a simulation toolkit called GN4. And GCR radiation, which is the main source of radiation in orbit, is made incident on this model. The imported CAD model is shown above. A full-scale 3D Monte Carlo simulation of 10⁸ events was carried out. The visualization of the GN4 simulation is also shown. The energy deposited per event on all the detectors is recorded and built. The resulting spectrum is convolved with a Gaussian and scaled appropriately. The plot here shows the GN4 simulated background of XSPECT, which is compared with the onboard background of another instrument called CLASS on the Chandrayaan 2 orbiter, which uses the same X-ray detectors. We find that the two spectra, the higher energy continuum are comparable, but the lower energy continuum deviates. The spectral lines that are generated are due to the particle-induced X-ray emission phenomena from the materials used. And the lines which are common to both spectra, their strengths differ. The differences in the two spectra are due to the different mechanical configuration of the payloads, including a non-Gaussian detector response for charged particles will greatly improve our result. As for future research, the contribution of the cosmic diffuse X-ray background will be added to the simulated spectrum. This developed model will be used on other space instruments like Helios and Aditya L1. It will also be used in determining the internal radiation environment of the crew module in Gaganyaan, thus enabling space exploration. Overall, we expect that the radiation background on board XSPECT will be at similar levels. For more details, you can refer to our digital poster or write to us. Thank you for listening.
Yeah, thank you, Dr. Kiran, for this development, because we understand that this XSPECT is one instrument which needs to develop with the Space Astronomy Group for the XSPECT satellite, and one more payload is being developed at RRI, correct?
Yes, sir.
Yes, yes. So, and you have brought out the capability of the Gen 4 simulations for this instrument. So we'll just see the questions are there from audience. 1-2 questions from the audience. Okay. Then Dr. Durga Rao, any point from your side?
Nothing, sir. We'll move.
Okay. Yeah. Then I have 1-2 points, Dr. Kiran.
Yes, sir.
So this in-orbit environment, because I understand that XSPECT is and this LEO satellite around most probably around 500 to 600 kilometer orbit, correct?
Right.
Yes. So here, what you are telling that in-orbit radiation environment simulations. So when we are doing basically, see, we have to take the flux and affluence all together. So because there are different particles of different energies all are available. So in this for electron, probably are you doing with equivalent 1 MeV electron kind of things, or just can you just highlight in this aspect?
This particular work, we have used only the GCR protons, which contributes to the most of the GCR radiation. But effect from other particles and radiation sources also needs to be added.
Okay. So but are you also dealing with the effect of these radiations on like other these equipments?
Right. This whole Monte Carlo simulation, the radiation is incident on the collimators on the top, and they will produce a lot of secondaries. All of that is actually contributing to the spectrum that you saw.
Okay. So very good. And what about this kind of the sputtering phenomena is also being studied?
Can you repeat that, sir?
No, I was asking about the sputtering phenomena also, because when you are talking about, let us say, when you are talking about the secondary particles.
Yes, sir.
So are you taking into account of the sputtering also?
Right. It is all taken care of, sir, because GIAN4 uses those physics lists, which takes care of all these things.
Okay, okay. Very good. Yeah, thank you, Dr. Kiran. It's a very good work. Yeah.
Thank you.
So, yeah, then please be with us. So we have 3 more presentations, and we'll go ahead with the next presenter, Dr. M.B. Dhanya from SPL, VSSC. So today she will talk on neutral mass spectrometer on articulated payload platform for spaceborne experiments. I understand that is a new developments at SPLs. So over to you, Dr. Dhanya. You have 20 minutes of time.
Yeah.
17 minutes presentation, 3 minutes question answer. Yeah, over to you.
Yeah, thank you, sir. I have shared my presentation and it is in full screen here. Hope you are able to see this.
Yes, yes, yeah, it is visible.
Okay, okay. Thank you. So today we heard a lot about the neutral mass spectrometer from the introductory in detailed review by Dr. Das, as well as a few other poster presentations. So I'll be presenting another aspect of the mass spectrometer, which is a measurement requirement on an articulated payload platform. So these are the team members from VSSC, and we have come together, the mass spectrometer team and the articulator payload platform, the details of which will come later. So these two teams have come together under the initiative of DTDI, called the DTDI Connect program. That's how we converged onto this project. So the outline, the scientific technical aspects and the implementation and the future plans. So why importance of the mass spectrometer? Why we need mass spectrometer measurements? Generally, mass spectrometer measurements are used for to study the upper atmosphere of any planetary environment, and also the exosphere of atmosphere, the so-called atmosphereless bodies. So upper atmosphere of any planet is an important region which undergoes the forcing from the sun from above and also from below in the form of several tides and waves. So upper atmosphere is a region which is continuously being modulated by processes from above as well as below. So these processes modulates the composition, temperature and other parameters of the upper atmosphere. And so because it is getting heated up and solar activity plays a role, so it is very important to measure the upper atmosphere composition as well as temperatures with respect to all these variabilities like solar cycle, season, solar zenith angle, latitude and longitude. And here this shows one typical example of Earth upper atmosphere from model results for the solar maxima and the solar minima conditions. These different colors represents the this y-axis is the height and x-axis is the number density of the molecules or atoms. And different colors of the curve indicates different constituents of the upper atmosphere like N2, O2, helium, etc. If we see this total concentration, this purple line, we can see that that itself shows a variation from the solar minima. If you see around 600 kilometer, that itself shows a variation from the solar minima to the solar maxima for almost about an order. So this is the kind of variabilities which exists in the upper atmosphere. And mass spectrometers are to measure this compositions and such parameters of the upper atmosphere. In situ measurements are very powerful. So in situ measurements for that enable the in situ measurement, the potential sensor is a mass spectrometer. And we have and mass spectrometers have been used from the early space planetary exploration era, starting from the liaison Apollo 17 for the moon. Moon is a body having an exosphere, and again on LADEE mission to the moon, and the Mars mission for the Mars we have the neutron mass spectrometer on the Maven, and then Saturn and other planetary bodies people have measured upper atmosphere using the mass spectrometers. That itself shows the potential role of the mass spectrometer to fill this gap area. And Indian missions, if we come to the Indian missions, mass spectrometer have been flown on missions like Chandrayaan-1, Mars Orbiter mission, and Chandrayaan-2. So as part of Chandra's altitudinal composition explorer, which was a part of Moon Impact Probe on Chandrayaan-1, and there was a MENCA, Mars Exospheric Neutral Composition Analyzer on MOM, and then a sequel to Chase-2 was flown on Chandrayaan-2 orbiter. And we have discovery class results from these observations, which include discovery of water vapor in the exosphere of the moon, and presence of gases. And similarly, on the environment of Mars, we have discovered superthermal argon atoms as well as distribution of the constituents in the exosphere during the evening time and during the global dust storm also. And from Chandrayaan-2 recently, we have obtained the global distribution of argon-40. So these shows that these kind of measurements they fill very important area as far as the science is concerned. And earlier we heard about the quadrupole mass spectrometer. So whatever we have flown on Indian mission are basically quadrupole mass spectrometer, and any component of mass spectrometer should have an ionizer to ionize the incoming neutral atoms, because basically we'll be sampling the neutral upper atmospheric components, neutral atoms or molecules, which has to be ionized for later detection techniques. So the techniques which we have flown on Indian missions, they make use of hot cathode dual filament, and which emit electrons, and the electrons impact on the neutral molecules and they ionize them. And there is an additional VA gauge, Weyerhaeuser Alpert gauge, which measures the total pressure as well. And these ions are guided through 4 rods with the alternating DC and AC potential, and only those ions with the for a particular voltage combination, only those ions with a specific mass group will only be allowed to pass through the rod and hit the detector, thereby constituting a current. And the detector assembly is basically Faraday cup with the channel electromultiplier to amplify the signal. So this shows the same. Is the cross section of the mass spectrometer, and the output of the mass spectrometer is basically we say mass spectra, spectral lines. Here the lines refers to in terms of mass in atomic mass units. So, and y-axis can be ion current or in terms of other like partial pressure or similar units. So in corresponding to each mass bin we get the signal. So they measure the relative abundance of the gas. That is very important. Now mass spectrometer, as mentioned, it makes the in situ measurement of the thermal atoms. And basically, they are low energy. They are thermalized population. They basically sample these population. So any contamination can affect our measurement. That is an important aspect. So any contamination from a nearby system can, since it can cause an unwanted signal, it is advisable to mount the sensor away from the spacecraft body. And also, since it is sample on a moving platform, this mass spectrometer samples the medium as it moves on the platform. For the better sampling, it is required to align the field of view of the sensor along the velocity direction of the spacecraft, which is called the ram direction, which requires that when we mount the mass spectrometer, this is one example, Maven mission. If you mount the mass spectrometer on a satellite body, say, if to achieve these two, first will not be possible if you mount on a satellite body, and in order to align the field of view, we may have to rotate the entire spacecraft, which is not in general not feasible. This is one typical example of Maven mission where they have used a platform which is pointed away from the spacecraft, and on which this is a platform on which the several payloads are mounted, and this platform has the capability to independently rotate, so thereby serving this purpose. So this necessitates these two requirements necessitate the use of an articulated payload platform. And Maven was a recent mission. This keeping the payload on a boom has been done even in the Apollo era. On Apollo 15 lunar orbiter module, it is done, where this mass spectrometer was mounted on a boom of length almost like 6 meters to avoid any possible contamination by the nearby systems. So in order to have this articulated payload platform, basically SPL and ASNT teams of VSSC, we work under the umbrella of DTDA Connect, where ASNT team of VSSC have been already working on a 5-degree robotic arm as a TDP, which you can see here. Basically, it is, I hope this video is visible. You can see that there's an elbow and a wrist, and this wrist has the roll and pitch movements, and this is the elbow, and this actuators here, they provide the required azimuth and elevation movements. So this robotic arm have been it as a part of technology demonstration. It has been developed for in general for an interplanetary mission with a very high torque output, and encoders were used for the feedback. And this we as a part of collaboration or requirements to meet the mass spectrometer, as a discussion, several experiments were considered to be mounted on this robotic arm, and we converged on the neutral mass spectrometer. And the parameters which typically define the robotic arm are kind of what is the type of the arm and how many degree of freedom. As you can see here, this has as this shown here, just 5 degree of freedom, and how many degrees of freedom we really need for the measurement, and the payload capability and workspace speed, how much accuracy it can provide, and the environmental rating and other parameters. So as you can see here, this is the robotic arm with the mass spectrometer payload mounted on it, and this is on a platform, spacecraft platform. So the now the articulated payload platform is being configured to meet the requirement of to mount the mass spectrometer and to carry out the measurement. So it should be able to carry a payload weight of around 6 kg, that too in the microgravity condition. And the robotic arm, length of the arm, it should be greater than 1.5 meter from the main spacecraft body. and it should have the capability for the azimuth as well as elevation scanning. And with the, as we all know, when we send it on a spacecraft, the power should be, it should consume minimum power. And then there should be suitable caging mechanism for the to arrest the launch load, and sufficient resolution is also needed for the feedback control. And we need the control system also to be mounted on the space satellite platform, and it should is optimized for a high mass to high torque to weight ratio. So the current scenario and the feasibility study showed that basically we have been collaborating with the different agencies within VSSC, if you can see, Civil ASNG avionics team, and then as a demonstration purpose, it is planned to fly this on a PS4 experimental platform. So we had to interface with the PS4 team as well, PSLV team as well. When we consider the programmatic linkage, this articulated payload platform with a mass spectrometer, after the demonstration in the PS4, it can be flown on any of the future missions of ISRO. And the basic in the feasibility study, we considered these aspects, which are the APP components. They should be lightweight links and interfaces, and then there should be suitable cabling for power control and payload, caging system, and then interfaces with the PS4 platform, as well as control system. Now coming to the actuator, which is very important aspect for motor, stepper and DC brushless motors were considered, and the torque ratio, and achieve the torque ratio, gear system, harmonic drive considered, and then for the feedback sensors, potentiometers or encoders are being considered, and there need brake as well as bearing systems. And the technologies involved shows that we need the high torque ratios, which are equivalent to one can see here 1,65,000 to 1:1 ratio in the actuator. And the design of we need to finally we have to miniaturize all these things. If we have to flow this on any of the missions, then miniaturization is an important aspect. And then using mini harmonic drive design, which has to achieve this 1:5,000 gear ratio, and the possibility of in-house design hollow actuators are being looked into, and the differential epicyclical gears as well. And then this shows the details of the mini actuators. So basically mini actuators are very, as we see, you can see here, is very small, and they are commercially available as well, and they are as we say, they are very small actuator. And coming to the hollow actuators, then requires there is hole through the actuator for the routing of the cable, and then it is ease of movement for the actuator also, and high range of motion for each actuators. And then coming to the differential epicyclic gearbox, high gear ratio comparable to this achieves, we get a high gear ratio when we compare to the mini harmonic drives. We can achieve the high gear ratio using this, and it can be cost effective as well. I think this will explain the differential epicyclic gearbox concept. So this is the way it works. And after considering this, then coming to the demonstration or mounting on the PS4 platform, we have to decide where to mount this on the PS4 experimental platform. So we considered 3 options. One is on the equipment bay. So it will come here. And then this will give us 3 degrees of freedom, which you can see here. This is the way it will be mounted. It will be deployed, and then it will have elevation and azimuth. And the another option was to mount it on the main satellite assembly desk itself. Then it gives us the advantage of 4 degrees of freedom. We can make use of 4 degrees of freedom. Okay, then there was another option was to mount it on the dual launch adapter. Then of these 3 options, we converged on the main mounting on the main satellite assembly deck was found to be more feasible with a 4 degrees of freedom. And then using a mathematical model, the torque requirement was simulated for the space as well as the ground condition. So for the different actuators, so different color indicates for the different actuators, and this is in Newton mm. So if you can see here, the maximum torque requirement is around something like 10 Newton meter in the space environment. So the design, by design we take almost 2.5 times for this qualification. So we have to design it for the 25 Newton meter torque requirement. So 4 degree of freedom and ground elbow on 2 actuators at risk for gimballing, and deployment is from the initial stored configuration to deployed stage, and then azimuth actuation for mass spectrometer, and elevation is also for the mass spectrometer. So we can see the deployment of the actuator here with the elevation and azimuth movements. So this is the azimuth scanning. And this shows the elevation. So the simulation shows the design, the way it is design is progressed, and it is capable to handle almost like a payload weight is considered to be around 5.5 kg, and it should work under microgravity condition and with a 1.5 rpm speed, and this is a maximum torque considered when less than 10 Newton meter. With the gravity, this is the value. This is in the space environment. And then power requirements for the motors and the mass spectrometers are considered separately, and for the encoders also. So now the implementation plan, this shows the actually what all activities are involved in the while finally arranging at the design level, taking into account the requirements from the payload team, as well as the for PS4 it is a PSLV team, and then make use of the working out the different design aspects, and finally converging on to the implementation. And as of now, we stand this is the milestones which we have to achieve is the ground test equipment we have to develop and then demonstrate the lab model, because now we have separately the mass spectrometer and the articulated platform available. Now it has to be combined together with all the requirements taken to arrive at the laboratory model where we realize the final hardware and including the control electronics. And here development of mass spectrometer means that with the proper interfaces, because now mass spectrometer on all the previous mission have been mounted on the spacecraft body. Now we have to work out the interface with the articulated payload platform as well, and then to the main satellite spacecraft. Then so how the electrical connections will be routed, and final assembly and deployment. And as of now, we stand that it is in the level 3, where the proof of concept level has been reached as per the NASA standard. This, as Dr. Das was showing in the his lecture, that about the technical readiness level. That's what it means. And then the necessary literature survey has been completed, and the overall configuration of the arm has been completed, and the design of individual subsystems are progressing. And so in the future, so this is a robotic arm in the laboratory condition, and then we have the mass spectrometer, and we connect, and finally we aim to realize this. So in the future development with the mass spectrometer, with the design of the actuator with the sufficient redundancy based on requirements, and then control algorithms we have to be achieved with the and guidance algorithm, and then we have to have the interface development for the PS4 platform, and then electrical routing study and robotic and gauging mechanism study. So these are planned for the near future. Thank you.
Thank you, Dr. Dhanya. It's a very interesting talk, and it is very happy to know the various developmental activities taking place on this aspect, that articulated payload platform. And it is a very innovative work, because first time we have been flying in the PS4, and after that probably I think we'll see the first flight in the Venus mission around 2025 timeline, correct? You may unshare the screen,
True.
Dhanya. I think that will be
Yeah,
better.
sure.
Yes, yeah. And okay, this is one thing I can understand from your talk is this articulated platform is required mainly to avoid a particle contamination from the outgassing from the main spacecraft, as well as to avoid magnetic field interference from the spacecraft, as well as the better sampling in terms of the field of view. So really with this development, we'll come up with various accurate in situ measurements of the neutral atmosphere, as well as the other ion atmosphere for other planetary bodies. So now the session is open for comment from my first. I will take up comments from my co-chair, Dr. Durga Rao. Just quick comments from you, Dr. Durga Rao.
Yeah, then it's a nice presentation. Developmental status also is very nice. TRL3 is there. Proof of concept also completed. Very nice, ma'am. Only thing is, I'm interested to know what is the robotic arm weight alone?
Material, sir?
Yeah, robotic arm weight apart from your
okay. Oh, weight. You mean sir, weight? Weight of the robotic arm.
Yeah.
Okay.
Sir, so Anirudh here, sir. I'm from ASMG, sir. So the current robotic arm which you developed in the laboratory, that is around 35 kilograms in weight. But sir, that is actually developed for interplanetary mission where we are supposed to handle high torque ratios. But for this arm which we are currently developing, as per simulation, it is coming under 9 kilograms, sir.
19 kgs?
So 9 kilograms. Sir.
9 kgs, okay.
9 kilograms. So that is purely the robotics, the robot component weight. We have not included the weight of control systems. That is yet to be configured. So the additional weight of the cabling and the control system also will come with that.
Okay. Nice, man. Yes, sir.
Thank you, Anirudh.
Thank you, sir.
Yeah. And any questions from the audience? I think there is no questions from the audience. Just 1 or 2 points from my side, Dr. Dhanya. Okay.
Yeah, sure, sir.
Yeah. So I understand that this is having this boom, or we call it articulated platforms, having around 1.5 meter length, correct?
Yes,
so
sir.
when it is mounted on the spacecraft body, definitely already I think the consideration might have been taken into account about CG, correct? The center of gravity. So just my point is when it is deployed, whether it is locking or otherwise it is retractable, because if it is once deployed, then okay, counter like CG calculation might be done, and it is retractable, then how it is being done? Just wanted to know. So kindly throw some light on this.
So actually, sir, we are working in tandem with the PSLV project also on this. So when we are developing a control system, so there are two aspects, sir. One, when the arm is moving, we need to give some counter motion to the PS4 platform so that there is a stability maintained. So we are trying to inject this as a part of the control system which is getting developed, so that PS4 platform also can balance the movement of the arm. And sir, the second part of the question is we have provided brakes on the arm so that once the arm is in position, it can be locked completely and there will be no movement from the arm side. So only the whatever during any instrumentation phasing, there will be no movement of the arm. So there it will be locked in a safe position. But when we are moving, we are trying to develop a control system which will take care of this movement of the arm. So as you said, the CG, wherever it is getting changed, the PS4 platform also has to give a counter moment. Am I clear, sir?
Yeah, it is very clear because I understand that it is a locking system. Once deployed, it is not retractable, correct?
Correct, sir. Yeah.
Okay. So, okay, that considers about this Kumar Misra from PRL. So, is Dr. Sajib available?
Yes, I'm available.
Okay, then yeah, over to you. You have 20 minutes time. So 70 minutes presentation, 3 minutes discussions. Time. Yeah, you may please upload the presentation.
Yeah. So just to confirm, are my slides visible?
Yes, it's visible. Yeah, please go ahead.
And yeah, okay. Thank you very much, Dr. Raghu. So I'm Sanjeev Mishra from PRL, and today I'll be presenting on this design and development of an instrument for electric field measurement in the planetary atmospheres. So let me just get my pointer. Yeah, so we have been working on this instrument for a few years, and this is the team involved, in which we have myself and our other colleagues. And this instrument was is being designed keeping in mind the atmosphere or the ionosphere of Mars. And since it was proposed and selected for Mars mission, which and we have started development for that purpose only. And as of now, we are also targeting to get this instrument ready and fly it on one of the PS4 platforms, which was, I think, discussed yesterday as well about the PS4 platforms. So coming to the scientific rationale and objectives. So Mars is different from Earth in one very unique sense, that Earth has this magnetic field, intrinsic magnetic field, which Mars does not have. So what that means is that there are a number of phenomena, especially the ionospheric loss and the atmospheric loss in general, that happens more on Mars and compared to Earth. And at the same time, the field lines that we see on Mars, they are not confined, unlike on Earth. And what that means is that the ionospheric electrons that are observed go as far as into the tail of the plasma. So the localized electric field that we see in certain pockets of Martian atmosphere, ionosphere. So what those electric fields do that they tend to contribute in the ionospheric loss. Basically, by accelerating the electrons or the ions, they tend to contribute toward the ionospheric loss. And this kind of phenomenon was also seen on many missions which were on Earth based, like S33, IC, and Freza. And likewise from Viking, what they say is that there is a particle acceleration which is associated with large amplitude and short duration electric fields. Okay, so these are the physical phenomena that are that happen on the ionospheres of Mars. And despite this, we do not have any direct measurements of low frequency electric fields. So recently we have had this Maven mission, which did give us some of the results, but this was not a direct measurement. It was more, it had derived some of the phenomena or the results. So this instrument will measure the electric fields directly. So coming to the measurement principle, we have gone with the spherical double probe, although there are two other techniques of detection of electric fields. So I have just put it here for completeness. So we have the spherical double probes, where you have two probes separated by some distance, and you measure the potential between these 2 points. And by using the knowledge of the distance between these 2 points, you get the information of the electric field along the direction of those probes. Okay, so it consists of experiments where a potential difference between 2 points in plasma are measured. And whereas there are other two techniques which were used in the very beginning, but they are no longer used, like the field bills, wherein you have a metal surface which is placed in a field, and then you make some current flow through the surface by exposing it for some time and then closing it. And then you measure how much charge it was collected, and based on that you try to infer the electric fields. And then there are the indirect measurements. These have a number of missions have used this, wherein they derive the electric field using measurements of other measurements. For example, the observed motion of charged particles and magnetic fields. These two are combined to generate to give us an understanding of the to give a picture of electric fields presence. Okay, so historically there have been a number of missions which have used the double probes, although some of them have used multiple combinations of double probes, like 4 or 6 double probes in different directions to get the X, Y, Z or some other orientation of electric fields. So we had this IC1 mission or GEOS, Freza, and Cluster on these missions. Most of them were on Earth ionospheres, whereas this Rosetta LAP, which went to this Comet 67P. So these are the frequency ranges that they covered. And what I have shown you here is the separation between the spherical probes. As you can see, it is 73.5 meters, 42 meters, 50 meters. So they were separated by a large distance. And why that is important is because when you are targeting, when you want more accurate results, like 0.5 or maybe microvolts per meter of resolution, so a larger separation between the booms helps. But in here, what we have is that we have this is the general block diagram where we have the two booms which are separated by a distance of around 3 meters or more. This is the design parameter that we are working upon. And then the two booms which are separated by 3 meters, they have these spherical sensors. These are basically Langmuir probe sensors, two sensors separated by some distance. And then there is a provision for guard electrode, and the wiring in this particular housing, we have provision for preamplifier here. And then the signal from the preamplifiers, both the preamplifiers, it comes down to the to get the differential to in this particular card, which is the front end FE front end card, wherein we get the difference between these two signals, followed by some sort of amplification by putting some gain, and then we filter the signals into various bands. And then after that, we digitize and send it for our backend card. Okay, so this electric field experiment is part of an overall experiment, that is Langmuir probe and electric field experiment. So we have the Langmuir probe as well as the electric field experiment combined. So both of them give this Langmuir probe gives us VSC, spacecraft potential, and NETE and other such data, whereas using this experiment we get the electric field measurements. So we combine the two data to generate a holistic picture of the phenomenon that are happening in the ionosphere. Okay, so I will be focusing more on the development of this front-end electronics card, along with some of the biasing and strip electronics that we have been developing. So the design requirements are that we have to be able to detect voltage differences of around 50 microvolts. That is the minimum that we are targeting to detect, to the upper limit of 1 volt. So basically, this voltage detection of this voltage difference translates into detection of electric field. By if I detect 50 microvolts of difference between the two sensors, sensor 1 and sensor 2, so I can say that the electric field in this region is 50 microvolts into 50 microvolts divided by 3 meter. That will be around 16 microvolts per meter or so. So the targeted detection of voltage difference is the reflection of the targeted detection of electric field. Okay, so the resolution of voltage difference measurements that we have targeted is 50 microvolts, and the filtering of signals have to be done in 3 bands: low frequency, medium frequency, and high frequency. And the expected electric field in the orbit is around 0.5 of microvolt per meter to 500 of millivolts per meter. Okay, and the frequencies are very low, around DC to 10 kilohertz. And in some cases, the frequencies of these fields can go up to tens of kilohertz, 40-50 kilohertz or so. Okay, so we started with the front-end development and the evaluation. We started with the very basic breadboard model, wherein we had the 3 channels and 4 channels for filtering. And then we moved on to our next version, where we printed the design on a PCB and tested it. And later on, what we found by evaluating a number of such live verification model is that the sensitivity levels were in the range of around millivolts, as you can see, at different frequencies. This is the minimum that we were detecting, and then we had to increase the sensitivity range. And then we had to evaluate the performance of instrumentation and differential amplifier which we're using. And then the frequency filter responses were also in need of improvement. So these are the design challenges that we had to implement in our next model, which we did. So this is the schematic diagram of our next model, where we had this preamplifier, differential block, and the gain stages. And then we have this. This is the low pass filtering, followed by the other 3 filter banks. And then this is the next version of the card, where we had given provision for these are the 2 channels, incoming channels, channel 1 and channel 2, from where we have the electric signal from the 2 sensors, followed by our difference amplifier and the instrumentation amplifier. So we have been evaluating the performance of the differential amplifier and the instrumentation amplifier to see which one will suit us the best, and followed by the filters that are implemented in these 2 ICs. Okay, and then in this particular card, we had also given the provision for current biasing using a DAC, and then we have also provision for switching between the gains. So the gains of this instrumentation amplifier can be switched. It can be programmed. So this is the populated card that we tested. And in terms of the performance, what we found is that the instrumentation amplifiers and the differential amplifiers. So what we see on these curves is that this is the difference voltage that we applied between the two channels. So 0.5 millivolts, suppose I applied 0.5 millivolts of difference between the two channels. So this is the obtained voltage that I got at the gain stage. This was with 85 to 4. Whereas similar when I applied the same difference of to this LM124, so these are the gain stage output that I obtained. So what we concluded is that the LM124, the differential amplifier approach using LM124 had some sort of limitation in terms of the minimum detectability. Whereas 85 to 4, with 85 to 4, we could detect signals as small as 100 microvolts or so. And this was the case when the signal differences were imposed on a very small signal. That is, suppose the means we have a DC signal of 100 millivolts over which we have imposed a sinusoid signal of let us say 100 microvolts. So the difference between these two can be detected here, whereas that was not the case for LM124. Likewise, for higher, when the signal values are higher, let us say 1 volt is the DC voltage over which we have imposed sinusoid signals of 100 microvolts or so. So in both the cases, what we observed is that the 85 to 4 had better performance compared to LM124. Of course, means we are carrying out further evaluations to confirm our confirm the results here, and then we'll move on to the next evaluation thing. And parallelly, we have also been, this is the filter response that we have implemented. What we can see for 3 filters, 300 hertz, and this other band, medium band, and the high frequency bands. These are the this is the filter response as of now looks optimal, although some further improvements are required in terms of the roll off. And next to parallelly, we have also been developing this electric field sensor. So it is basically for the lab testing. We have developed this sensors which have this Teflon for separating the electrode main sensor from the guard electrode. So this is the electrical connection. It shows how we had a shielded cable connected to the sensor surface. This is made of aluminum, and we have used this sensor to test our electronics. So these are the sort of tests that we conducted in ambient, where we had the 2 sensors mounted on this is a PVC pipe we have been using just to test the functionality of these 2 sensors. And we have these are the sensors as fabricated. These are different sensors to what you have seen earlier. So we had a number of iteration in terms of design and development of the sensor as well, which I am not going into detail. But the final sensors that we have been testing as of now, these are the ambient electric fields that we could detect by applying some sort of electric field to these. By exciting the sensors with electric fields, we could see that the difference, whatever difference we could pick up, it can be seen. So next, what the future work involved in this instrument is the detection sensitivity of 100 microvolts needs to be brought down to further. And then we have to decide on 85 to 4 versus LM124, which means as of now the testing is going on. And then the functional testing of the version 2 is also underway. And along with the analog filters, we are also targeting to develop digital filters, which we are developing in MATLAB, which will be implemented on DSP. Since we are targeting to send this instrument on PS4, so as of now, we are thinking of implementation of digital filter on DSP, whereas for actual mission on Mars, we'll be using FPGA. So both the implementations we are looking into, and parallelly the development is undergoing. So backend processing card is parallel for this electric field experiment as well as the LP experiment, which this experiment is part of. So that is also being implemented in parallel. So thank you to all of you. If you have any questions, please ask.
Thank you, Dr. Sajib Kumar Misra. So it was a very good talk on the design and development aspects of this instrument. We understand that is a new development because You have highlighted about electric field measurements on both direct and indirect, and we understand that from the talk that PRL has undertaken the spherical double probe, that is direct measurement, correct? So development is on that only. And just one questions I have with this like a discussion only. So how you are taking into account of this space charge effect? So when you measure these two actually the probes, and how does it affect the accuracy? Because you have mentioned about you have achieved 100 microvolt at 1 kilohertz kind of things. So the space charge effects, are you doing such kind of neutralizations in between, or can you just highlight on this?
Yeah. So the numbers that I have shown here, these are the numbers for measurements made in the laboratory. So the space charge thing that you're talking about, yes, it will be a factor when the instrument goes on the satellite. So to neutralize that, what we have to do is that we have to make sure that the conducting area, we have to give some sort of conducting area to balance the basically current balance has to be there. So the current balance, that the current that is flowing out of the probe, whereas the current that is collected by the space, those two have to be balanced. So for that, a conducting area sort of will be required. But as of now, these numbers that you see, it is only for verification of the functionality of electric field. Electronics. Yeah.
Okay. Thank you. Definitely, yes. Plan is very good that it will be taken care during the realization of the actual flight model. Correct?
Yes, that is true.
Yes, thank you. So now the session is open. I want to hear the quick comments from my co-chair, Dr. A.M. Durga Rao. Over to you, Durga Rao.
Yeah, sir, here two small questions I have. So here the dynamic range is very wide. You said that it is from few microvolts to few millivolts, because as it's in case of measuring the electric field. So and also by using two devices, LM124 and AD524. So one is good at higher dynamic, handling the higher level of signals. Other one is a little bit better when you are handling lower signals. In order to balance these things, usually do you have are you having a plan of handling with two channels or with a single channel itself? You will be optimizing these two, managing your dynamic range.
Yeah. Your question is absolutely correct that there are two approaches. Since the dynamic range is too large, so single approach will not be working for both the cases. So as of now, that is why in the latest version we have provision for both the approaches. We have LM124 as well as AD524. So what we plan to do is that we plan to have switchable, so that at different in different regimes, we can switch between this method or that method depending upon the plasma conditions. So we have to switch between these two methods. As of now, it is not decided, but yes, it is true that we have to have provisions for both the cases. So most probably we'll be going with both the cases, and later on, if we find that there is some technique which can cater to the whole dynamic range in a single scheme, so maybe that can also be implemented. But as of now, I think both the schemes will have to be going in parallel.
Yeah, and one more small doubt. See, when the electric field that levels are very high, so that is not in our hand, because suddenly if you are unexpectedly large signals when you're receiving, whether are you safeguarding your instrument by you are limiting your input signal to a level?
Yes, means in terms of electric field levels, if they are very high, what we have in the very beginning at the sensor is this preamplifier, which provides a very high input impedance to the incoming signal. So that will also work as to isolate the incoming signal from the rest of the circuitry. So that high input impedance amplifier as at the preamplifier is what will be guarding the high levels of signals.
My question is, are you limiting to a maximum level? That is what my doubt. Or what is the maximum level that you are limiting?
Limiting in the sense, means what I understand.
Your sinusoidal signals, whatever differential amplifier outputs are coming. So once it goes to, do you have like a limiter circuit or some other thing you are implementing?
Yes.
So
yeah, so means we are not implementing any limiters, but when the signal goes above, for example, design range is 1 volt per meter. So when the electric field strength is more than that, so it will be just saturating. We'll be getting the saturation data. Basically, it will be reaching the saturation of the ADC, and ADC will be showing that it is out of range or maybe maximum voltage. We are not limiting as of now. Yeah.
Okay.
Yeah. Thank you, Dr.
I'm
Durga Rao.
here.
Pardon?
I'm Satish Thambi from SPL. Can I ask one question?
Yes, please. Go ahead.
Yeah, anyway, it is a very good work. I appreciate the effort taken by PRL. My question is actually, see, normally people used to go with the conventional dipole or monopole antennas for these electric field measurements. So what actually prompted you to go to the Langmuir probes with a certain distance? This is my first question. Second thing is, now this you are planning for PS4 as well as for the Mars. So whether have you done any estimate of the field strengths and what sort of different fields which are prevailing in that different environments? So whether this the length or the probe which you designed is catering to the requirements which you are envisaging for meeting the scientific requirements?
Yeah, sure. So I'll answer the second question first. So regarding the expected signals that we are going to see, whether on Mars or on Earth, for Earth we have enough data. Basically, we are targeting to, based on the plasma composition and based on literature, these are the voltage ranges, electric field ranges from around 2 to 3 microvolts per meter to minimum to around 1.5 volts per meter maximum. That is for Earth, whereas for Mars also the estimates based on some of the modeling as well as some of the indirect measurements, that is also around 1.5 to microvolts per meter, or in some cases it can go less than 1 microvolt per meter to around 0.7, 0.8 at max 1 volt per meter. So these are the numbers within which we are working. And for the first part, that why we have went with this double spherical probe with some distance, the reason is that this is the technique which is which the theory and the implementation of it is very straightforward. And the presence of two spherical probes, what that does is that when you have single probe, so it is prone to spacecraft rotation. Spacecraft can come into its wake, or maybe the symmetry of the probe may come into picture. Whereas when you have double probes, so the symmetry is maintained. At the same time, the effects of spacecraft wake or the orientation of a spacecraft, those things are minimized when you have spherical double probes. So these are the reasons which make the implementation as well as the data analysis of it comparatively convenient. At the same time, we had this LP experiment wherein we had one single probe, one single LP. So since we have a single LP, along with that having an electric field measurement, having two spherical probes, the one of them can also work as a redundant probe in case the LP does not work, or as a redundant, it can also work as an LP probe, the two electric fields. So these are the reasons why we went with this double spherical probes.
Fine. The only concern is actually, see, when it is coming to a ionospheric condition where actually too much plasma is there, actually with a large collection area like LP, whether it really accounted the dB shielding effects as well as other related. They are saying whether accounted. If you are putting in a PS from say for 300 or 400 kilometers, so what is that expected signal level there? Other thing, Mars case actually it is totally different. So now this instrument which you are designing is meant for both. So whether you are accounting that, that's all I wanted to know. Anyway, fine. You are taking that
you are correct. We are accounting for all that. The sensor design as well as the once it goes for mounting on the deck, so all those requirements will come into picture. We are working on all that. Yes.
Okay, fine. Okay. Thank you.
Thank you, Dr. Satish Thambi and Sanjeev Kumar for these interesting discussions about the intricacies of this instrument while measuring these magnetic field aspects. So, is there any further questions? We can take up only one questions because we are running short of time. We are entering the break time. So, otherwise, we'll move to the next speaker. We'll thank the speaker, Dr. Sanjeev Kumar Misra, for the very interesting and insightful talk on this electrical measurement. And we know that electrical measurement instrument is very new while we're considering about instrument about ISRO instruments for planetary explorations. So
thank you, Dr.
good luck. Yeah, good luck to the team. Yeah. So then we'll move to the next presenter, Dr. Abhishek JK from SPL VSSC. So his topic is an experimental study of the response of the space-borne channel electron multiplier detectors. So he'll be talking on the channel electron multiplier detectors to intermittent high helium ion flux. So is the speaker available? Abhishek, over to you.
Yes.
You can please upload. Yeah.
Can you hear me?
You have 20 minutes time.
Can you hear me there?
can you hear me there?
No, we can hear you, but audio is feeble. And please upload the presentation, then we will see. Yeah, now presentation is seen.
Can you hear me okay? Is my voice clear?
Yes, yes, audio is volume is very less. Presentation is seen clearly, no issues. You may come closer to the mic. Speaker.
Now.
Yeah, it is better.
Yeah, so I'll be discussing the one of the most popular detectors in sort of particle instruments nowadays. That's the channel electron multiplier detectors. Now, yeah, for channel electron multiplier detectors, they can detect electrons, ions, X-rays, UV radiation, and more. Now, on the figure on the top right, you can see two typical CM detectors. They're quite small. And on the figure on the bottom right, you can see a cross-sectional view of the CM detector. It starts with a wide channel, and it gets progressively thinner as you go into the length. Now, detection happens through photon-induced secondary electron avalanche or charged particle impact-induced secondary electron avalanche. That is, a particle comes and hits the surface, and there's a voltage applied between the two plates here. And the initial strike creates an electron, and that multiplies along the surface. And at the end, we get a collection of electrons. One moment.
Abhishek, can you make it a little louder and full screen? Yeah.
Yeah, one moment. Let me. I just try reconnecting one. Yeah.
Hello.
Abhishek.
Hello. Can you hear me now clearly?
Yeah, yeah, it is better. Better than the earlier one. Yes.
Satish sir, can you hear me now?
Yeah, we can hear
yeah,
you,
yeah.
but presentation is not seen.
Okay, one moment.
How
about now? Is it?
Yes,
yeah,
it
it's
is
coming
seen
now. Yeah. Yeah. Good.
Yeah. So all right. So as we were discussing, it can detect electrons, ions, and ions, X-rays, and UV radiation and more. And the detection is through impact or photon impact-induced electron avalanche. So as you see on the figure on the bottom right, there's a glass capillary tube with a length to diameter ratio between 50 and 100. That is, it's very long and thin, and it's winding here. Now, a layer of semiconducting material with high secondary emission characteristic is deposited on the interior. So that helps in the avalanche of electrons. Although we are hitting one particle in the beginning, at the end we get a multiplied pulse. Now, these are typically operated under a vacuum of 10 power minus 4 millibar or better, and it gives a gain of 10 power 4 to 10 power 7 in counting mode operation. Now, if we operate it at higher pressure, there is a chance of sparks and voltage shorts and a damage to the detector. Now, these detectors are used in industry as well as space missions. Now, in the industry, you will see that they are used for leak detection, that is mass spectrometers. We will see them in chemical factories and airports. They are used in electron microscopy. They're used in semiconductor manufacturing as well as night vision and other applications in the military. As for space missions, they have been used in plasma instruments. For example, in the Cassini mission, Chandrayaan-1, as well as in the MAVEN. They're used in the neutralizers aboard MOM, as well as Chandrayaan-2. They have also been used in X-ray spectrometer payloads. This is a solar X-ray spectrometer. It's a NOVA instrument. Now,
A bit more detail on the CEM detectors about bias, output, and IV characteristics. So the figure on the top right shows you the typical bias schematic of the detector. It has 3 terminals shown here. Now the front terminal, it is biased often at ground for electron detection and at negative 2000 volt for ion detection. And this is the anode. The anode is the point where from we collect the charge pulse. So sometimes the anode is at high voltage, that is 2000 volt in case of electron detection. So to get the signal separated from the high DC voltage, we use this separating capacitor. This is a DC booking capacitor. And we use a combination of resistors here to make sure that the anode is at a higher potential than the backplate here. Now, the bias schematic, what it looks like in the lab, is shown in this figure on the bottom right. You see that the front plate is biased using this cable, and the back plate and the anode are here. And the anode, the signal is taken through a capacitor. Now, this figure shows a typical CEM output pulse. Now, this pulse has an amplitude of 60 millivolt, and it has a width of roughly 8 nanoseconds. Now, the figure shows the typical IV characteristic of a detector. We apply a voltage of 1800 volt to 3500 volt safely on the detector. So the x-axis shows the bias voltage, and the y-axis shows the bias current is in microampere. So if we see that for 2000 volt, we have roughly 30 to 35 microampere current. So it offers a resistance of 50 meg to 500 meg. And the dark count, that is the input, the output when there's no input, it's less than 10 counts per second at room temperature. As the temperature goes higher, the count increases, dark count increases. Now moving on to a bit detail on the pulse height distribution and gain. Now what's pulse height distribution? So in case of these CEM detectors, we have a primary particle creating secondary electrons and leading to an avalanche and the pulse at the end. Now, if the on the first strike, if the number of particles emitted is more than 1, then the output also increases correspondingly. And even at any step, the number of particles emitted can change. So this is quite an unpredictable process. So the randomness inherent in the electron avalanche, it results in a fluctuating gain, even when the input and bias voltage stays the same. So what does that mean? So let's examine a scenario here. Now this represents the CEM detector with a bias voltage of 2000 volt, and this represents a sample particle. And on the first strike, we see a typical pulse of this amplitude, and with all the conditions remaining the same, the amplitude is higher here, and it goes even higher here. And on the fourth strike, it is less. So this is due to the randomness inherent in the avalanche process. Now, due to this avalanche randomness, if we plot a histogram of the output pulses, we get a distribution, which is seen in the middle here. Now, this is known as the pulse height distribution. On the x-axis, we have the amplitudes, which ranges from 70 millivolt to 130 millivolt. And on the y-axis, we have the counts. And we see that most of the pulses are peaking at 110 millivolt, and there's a spread with an FWSM of 11%. That is the full width at half maximum. Now, how the pulse height distribution varies with increase in bias voltage is shown in the figure on the bottom right. On the x-axis, we have again pulse height, and y-axis counts. We see that for the green PhD, that is at 2200 volt. The pink one has at 2800 volt. We see that the peak shifts to the right. That is, the gain increases as the voltage increases. Now, how this is measured in the lab? This is measured in the lab using, it's shown in this schematic. Now, the CEM detector is housed inside a vacuum chamber, and the input is provided using electron as well as ion guns, or even using a pressure gauge, or even a UV lamp sometimes. Then the high voltages are supplied using a power supply, and then the output of the detector is taken to an oscilloscope or a multi-channel analyzer, and the whole system is controlled remotely. Now, what makes these CEM detectors suitable for satellite applications? The fact that they are rugged, that they can withstand vibration and shock, as well as thermal stress, due to they are enclosed in a ceramic container, as you could see in the first figure. So they can withstand all the stresses. Now the picture on the right shows the PAPA payload, that is plasma analyzer package for Aditya, which contains the CM detectors undergoing a vibration on the vibration stand, and it must withstand a vibration of 8.5 G thrust and 7.9 G on the lateral. Now they also should be radiation tolerant. Most of these payloads or satellites pass through the Van Allen belts. Although they may not be operated during the passage, they should not be damaged due to the radiation. So for that, we test them at high energy radiation. So the picture on the bottom right shows how we do that. So this is a 14 MeV beam line, the proton beam line, and this picture shows how the electronic components are mounted to expose to the beam line. This is done in BARC in Mumbai. So they should withstand a displacement damage dose of 10⁸ MeV per gram to qualify for this flight. Now another plus point of CEM detectors is that it is not outgassing. So for satellite applications, when we launch into vacuum, we should ensure that the volatile content is very less. That is the TML, that is the total mass loss, and CVCM is the collected volatile condensable material. These are essentially indicators of the volatile composition. So they should be very less. So if the volatiles are high, what often happens is that we contaminate other systems in the satellite and generate spurious signals. And another positive is that the CEMs are non-magnetic, and they don't interfere with low current systems, which are often found in the satellite. And CEMs also consume less power, and they have very low mass and size. And they also manage to survive through the life of the mission. Now, as for the lifetime considerations, so we need to understand how the CEM is sort of operated in the plasma instruments to understand what is the meaning of lifetime in the CEM. So oftentimes CEMs are followed by a constant fraction discriminator, which essentially converts the pulse of the CEM to a digital pulse. So if you pay attention to the bottom left figure, we see that the yellow trace indicates the CEM pulse, that is analog pulse, and the pink trace indicates a digital pulse. So digital pulses are easy to count. So what we do is we feed the digital pulse into a counter. Now these constant fraction discriminators, they have a input threshold. So if the output of the CEM goes below this input threshold, then the effective life is over. So that is the first end of life scenario. That is, the gain falls below the preamplifier threshold. Now the second end of life scenario is the maximum safe bias voltage limit is reached. So to understand this, we have to look at this figure on the top right. So this is essentially a result of an accelerated life test on a CEM detector. So for every charge strike, a detector emits 10⁷ electrons. So that means a limited amount of material is lost on every strike. So since the CEM can only lose a particular amount of material over its life is limited by the number of strikes. So on the x-axis, we have the accumulated counts in units of 10⁹, and on the y-axis, we have the detector bias voltage. So as the accumulated counts increases, the gain drops, and we have to increase the bias voltage to maintain the gain at a constant level. So although we started off with a 2.5 kV bias, at this point we have to increase to 3.1 to maintain the gain, and at this point we have already reached 3.3 kV. Now the safe operating voltage is up to 3.5 kV. So the remaining life is only this much. So that's the second consideration. So in the test that we did at the lab, we were interested to find the gain variation with flux exposure. So we followed up a study conducted in 1967 in which the two detectors were exposed to different steady count rates. So the dotted line indicates the 3000 counts per second flux, and the solid line indicates 6000 counts per second. So the gain falls dramatically in the beginning, as you can see in the next figure, that's the figure on the right. So initially up to 40 hours, the gain falls very sharply, and after that it settles to a constant level. So we see that 3000 counts per second detector is set to a higher gain than the 6000 counts per second exposed detector. So the questions which arise when we use it in space, how the sudden flux spikes due to a phenomenon such as CMEs can affect the gain, and what are the long-term implications of these flux spikes on CM. So to understand this, we expose the detector to 100,000 counts per second flux. So we started off with a detector at this gain, that is 3 into 10 power 7 gain, and we exposed it to 100K counts per second. And within 3.5 hours of exposure, we see that the gain has dropped to 1/3 roughly. So it started acting as if it is it has been exposed to a steady flux of 6,000 counts per second. And the second thing which we wanted to investigate is how can the gain be maintained even though the flux may be a little high. So what we did is we exposed to 10,000 counts per second intermittently. That is, for every 2 hours we exposed it to half an hour of flux, and we also gave it periodic breaks. That is 48-hour breaks outside vacuum when the detector was not powered, and we see that the gain is not falling as sharply as in a constant flux. So these blue points indicate that the gain is more or less stable. Now, to get into a little bit more detail on how the detector is responding to high flux. Now the flux level was 100,000 particles per second for 3.5 hours, spread over 15 hours. So the detectors were biased at 2,300 volt. Now the figure on the top shows you the pulse height distribution before the exposure. We see that the average pulse height is roughly 70 millivolt. Here you can see here, and we did this for 3 different detectors. And for all the detectors, we see that the pulse height is higher. And after the exposure, we see that the pulse height has dropped to roughly 15. So the damage is permanent in these detectors. Now in this figure, the top two remaining the same. So we want to understand how can we recover the gain, although the damage is permanent. So in this case, we increase the bias voltage to 2,700 volt, and we see that the gain has recovered to previous levels. So although the gain loss is permanent, increase in the bias voltage can recover some gain here. Now the second scenario is exposure to intermittent low electron flux, and the blue points which I showed you. So we wanted to see how can we maintain the gain even though the exposure is steady without decreasing the voltage. So here the top panel shows the so we did this for 500 hours. So x-axis is the number of hours here, and on the top panel the y-axis shows the average amplitude. So in the beginning we started off here, and at a steady exposure the gain has dropped, and here we gave a 48-hour break, and we see that the gain has recovered and the gain is more or less steady. And at this point we increase the pressure in the chamber, and we see that the gain has dropped again. And this is again a 48-hour break, and the gain has recovered. And we see that after about 250 hours, we see that the gain is more or less stable, even though we gave a break, and there is a sudden increase here. The gain has suddenly more or less come down to the same level. So after 250 hours of operation, the gain is settling to a constant value. But here the point to note is that this 48-hour breaks, they do manage to recover gain even without increasing the bias voltage. And on the panel 2, we have plotted the amplitude on the y-axis and the frequency of occurrence of these pulses. So this gives you an indication of the, it's an indirect indication of the full width half maximum. The brightest regions, that is the brightest white regions, indicate that the pulses are very narrow, and the dark regions indicate that the pulse height distribution is broad. So we see that in the beginning, pulse height distribution is narrow, and intermittently they are narrow, but there is no correlation between the pulse amplitude and the pulse pulse full width at half maximum. There is no particular correlation because, for example, in the beginning this is high, this is a high, but again this goes high, but this does not rise up. So these are also not correlated. And on the third panel, we see how the pulse width is correlated. If there is any correlation between pulse width and amplitude, as well as at the full width at half maximum. So here again, we have plotted pulse width on the y-axis and the frequency occurrence as a color plot. And we see that there is a very less correlation between pulse width and amplitude. When the amplitude is high, we sometimes see that the pulse width is high. But even at this point, we see that although the amplitude is high, the pulse width is low. So these are also uncorrelated. So,
Dr. Abhishek, you have two more minutes.
Yeah, it's done. It's done.
Yes,
so
yes.
what the conclusions from the study? So we conclude that the sudden spikes lasting up to half an hour at a time in the incident flux can bring down the gain of CEM detectors permanently. Flux spikes can mimic the effect of long-term steady flux on detector gain. And there is no long-term implication on CEM detectors due to spikes apart from the drop in gain. That is, they are still usable. Then the gain drops under steady flux can be reversed to some extent using controlled exposure of CEM detectors to standard atmospheric conditions. And there is no evident correlation between the pulse amplitude and pulse width of the CEM during a steady flux input. That's it. Thank you.
Thank you, Dr. Abhishek. It's very interesting developments on this channel electron multiplier detectors, and it is quite efficient because you have mentioned about the dead time can be as less as 10 CPS, correct? So, yeah.
Dead time, yeah.
Yes, yes. So it is actually very efficient detector, and it is very good development, and all the actually tests you have conducted at different the fluence level also gives the very robustness of the system being developed. So just 1 or 2 points we'll just hear from audience, and then first I want to hear from Dr. Durga Rao.
Sir, not much, sir. We can take from audience.
Okay, okay, fine then. Just 1, 2 points from questions from the audience if anybody is having questions.
I'm Dhanya from SPL. Can I ask one question?
Yeah, please go ahead.
Yeah, Abhishek, it was nice presentation. Then in the space, how do you suggest that CEM should be operated? Because in the space, we will see varying particle count rates. So do you suggest that we should not operate it for continuously for long hours, or should operate intermittently? So what is the suggestion?
Yeah, in space, we already have a built-in brake mechanism. What happens is that since we are scanning these, for example, in say Papa or Sarah, we have a scanning mechanism of energy. So there'll be high fluxes at say 1 keV, right? And there'll be very low fluxes in most of the other energies and most of the other directions. So the CEM detector will see high flux only for a fraction of time. So there's a built-in brake, when we are scanning. But yeah, if we are using it for a steady operation,
so if
you're using it for a steady operation, it's better to keep the count rate low. Yeah.
Okay, yeah, got it. Thank you.
Yeah, thank you, Dr. Dhanya. Any questions from? Yeah, okay. So one question from in the chat box, Dr. Arpin Patel from PRL only. So why some of the bins of the degraded spectra show 0 values?
Why
Over to you, Abhishek.
Yeah. Yeah, here what we have, okay, I'll just share my screen once, I mean, so that we can understand. So I guess, okay, so can you see the screen?
Yeah.
Hello. Yeah, so
yes,
I
yes,
think,
we can see,
yeah,
yes.
he's talking about the gaps here, right? So, so what's happening is that we are binning these values into roughly 100 bins. So in some amplitude regions, say, I mean, we have a pulse of 15, then 16. There may not be a pulse of 17. So that bin will be 0. So that's the reason.
Thank you, Dr. Abhishek. I think, yeah, so he has typed that it is okay. So that means he is convinced with your answer. Thank you. So
thank you.
I think now we have time to conclude the session because the session is so interesting that we don't know, it is already almost 4:30. Next session is about to begin. And we already had eaten up for the break time also. That shows the how much the session was giving a lot of information as well as interested to all of us. So now I take the opportunity to thank all the speakers. We have 8 talks in these sessions, and a lot of interesting debates, questions, and understanding. If you have further questions, you may please send to the local organizing committee. We'll forward to the speaker so that we'll be in touch. So if any other points from my co-chair, Dr. Durga Rao, I think I will formally conclude these sessions, and I will hand over the next sessions to Durga yourselves and Dr. B.K. Rana, because you both will be sharing the next sessions. So any points from Dr. Durga Rao?
Yeah, very nice, interesting talks there from all the participants, and we had a very nice time sharing a co-chair with you, sir. I think because time is already running up, so there is no much point, sir. We'll conclude the session, and we'll be get ready for the next session.
Right. Okay, then formally, then we'll go to the next session, session B. Then we'll meet again, and probably I think we have other sessions tomorrow and day after tomorrow, which begins at 2 p.m. and 4 p.m. at the same time. And we request all the presenters, whether you are presenting or not, please be available with these National Space Science Symposiums. And then together we have to make the event successful. Yeah. Thank you all. It was my pleasure to meet you all. Yeah. Thank you.